Richard Attenborough.
Oh yes, David
Yeah.
Attenborough for the
I get confused with
the biology. Yeah,
Attenboroughs.
Richard
Yeah.
Attenborough. Yes,
Yeah.
the two, they're brothers.
David Attenborough.
Yeah.
Yeah.
Brazil and polar everything.
So I'm assuming we're in physicist world where everything starts a few minutes after the hour. Is that correct?
Yes.
Yes.
Okay. Should I stop the share for now, or just?
No. Just
ahead.
your screen, just to save the time. No, not and I also can read your title.
Yeah. You can put full screen. It will be better.
I wish.
Yeah.
Perfect.
Excellent.
Yes, thank you.
Okay, perfect.
Maybe you can, because now we can be sharp today. Hello, everybody. It is my pleasure to announce the seminar by Andrew Liddle with his quote. He will tell us his quote himself, and a little bit unusual title, unusual subject for today, biocosmology, towards the beginning of a new scientific topics. Please, 1 hour.
Okay, thank you very much. It's a pleasure to be invited to talk. And of course, I'm really an astronomer and not a fundamental physicist, but I'm going to be talking quite a bit about some fundamental physics issues as we go through. And I know that many of you are much more expert in these. So I'm really hoping that me and my collaborators will also be able to learn from how you receive what we're saying, what your opinions are, and just trying to learn as much as we can from you. So what I'm introducing is a topic that we call biocosmology, and it's definitely a significant departure from many of the things you traditionally hear of in this seminar series. I've looked at your past talks, obviously with strong focus towards quantum gravity. Here, the purpose is to discuss fundamental physics, but from a very different perspective that comes from taking inspiration from living systems and biological systems and seeing whether or not there are lessons to be learned about that might inform how we think about physics and even how we might think about cosmology, which is my own specialist subject. So we've taken a long time to bring this to fruition, but we submitted our first 3 papers on the topic of biocosmology in April 2022, the work having started maybe 3 years before that, when Marina Cortege first came up with the idea of biocosmology and of adopting living systems and assembled our collaboration in order to try and develop the ideas. It took us a long time to come to a common view within the collaboration, even of what we were trying to do and certainly how to try and achieve it. And I can only tell you little bits of that story, I think, during today, but I will do the best that I can. So first of all, the motivation, the thinking behind this is to reformulate or interpret physical laws in a way that directly allows the inclusion of biological systems. Now, I think many physicists and cosmologists think that they are already doing this in everything they do. We argue otherwise. We argue that we can take inspiration and may need to change our thinking based on information coming from biological systems. The tools we'll be using are, well, unfamiliar, I think, to most physicists. We discovered them through our collaborator, Stuart Kaufman, who is a theoretical biologist, a very renowned theoretical biologist. He's one of the MacArthur Genius Award winners, so that gives you some idea of his status within the field. And he, amongst his many ideas, is the idea of the adjacent possible, which he published on from around the year 2000 onwards, which envisages the evolution of complex systems on the basis of where you stand at any given moment. So the adjacent possible is the places you can readily reach from the place you already are. And this is a very general idea. You might apply it to biological systems and say, where can evolution take the elements of a biosystem forwards? But there's also been many applications of this idea in economics, in patents for inventions, generally speaking. To invent something like an airplane, first you have to invent engines, wings, ejector seats. other things like that. And you're always expanding a wave through the possible. So parts of the adjacent possible become actual, they're realized in our world, and then the adjacent possible moves on. And so it's like a rippling wave passing outward. One particular implementation of that, of the adjacent possible, is called combinatorial innovation, and I'll say a little bit about that later. Now, part of the key to this thinking, which immediately makes a lot of physicists nervous, is that we will be challenging the normal physics assumption of reductionist behavior. I'll come back to that again as well, not a bit in more detail, but it's worth putting it up front so your heads can already start to be thinking, what on earth is he going to be talking about? Physicists, particularly those experienced in fundamental physics, like most of the audience here, are used to the idea that if you want to understand something, you break it down to its smallest elements. And if those elements are not small enough, you can try and improve your understanding further by digging in even deeper to the smaller, to the higher energy. Biological systems show us that physics is not necessarily amenable to that kind of treatment. How do we start this? Well, what we're going to do is seek to quantify, first of all, the biosphere using a language of physics. This is a kind of entry portal into the topic of biocosmology. It's the route that was taken first by Marina, to try and judge the information content of the universe and put the biosphere into the same context as that and see what comes out. So this is the general principles, and I'll be trying to expand on all of this as time progresses through the talk. Here are two of the papers. So to introduce our collaboration, Marina, as I've said, is the initiator of the topic. She's the kind of leader of the whole biocosmology project. She gave the first seminar on the topic at Perimeter Institute when we were visiting there in November 2019. And she then recruited the team to try and develop the ideas. Stuart Kaufman, I already mentioned, is a theoretical biologist who has the MacArthur Prize, has worked mainly on complex systems, written lots of books. I'm the one who's talking to you at the moment. I'm a cosmologist, now based at University of Lisbon. And many of you, given the topic here, will know Lee Smolin, our collaborator from the Perimeter Institute, who's obviously one of the leading figures in the field of quantum gravity, and also a very broad thinker about the nature of fundamental physical laws. So we have a very strong team, I like to think, I hope you agree, for trying to investigate these very novel ideas that are being put forward. Now, it so happened that because we liked the idea, we wanted to have as much fun as we can from biocosmology and broadcast it widely to people. We thought that when we finally had the papers out in April, we would hold a press release and have a bit of publicity to go with the topic. It turned out that at that time, Marina was in Nepal at Everest Base Camp because she was part of an expedition climbing Mount Everest, and was in the early phases of preparation for the summit attempt at that point. Here, there's a couple of pictures of her on what's called an acclimatization summit, where you try to build up your tolerance to the reduced air in the atmosphere. This is on Lobuchi Peak, which is already 20,000 feet, so a fairly substantial elevation, but still 10,000 feet less than the summit of Mount Everest. Which unfortunately, a month or two later, she was not quite able to reach. She was attempting to summit without using supplementary oxygen, and on this occasion was not able to succeed to get all the way to the summit. But there are many stories around that can be said another time. Anyway, at this point in April, we wanted to have some fun making a press release for the papers. And we thought, why not broadcast the press release live from Everest Base Camp? With Marina there. And we've got a couple of videos, and I thought it would give a flavor of the thinking and also give Marina a chance to say something about the biocosmology. If I just played a couple of these videos very briefly, there's two, I'll cut off one of them quite quickly because it's more introductory, just so you can hear a little bit from her. I'm hoping the sound will be okay. The sound, I think, has to come out of my speaker and back into my microphone, and so I hope I've got it set up okay. If you can't hear it, then I'll cut it even more short. Just tell me it's inaudible. Okay.
Hello, good morning, everybody. This is Marina Cortez from Everest Base Camp. Here in Nepal, it's about 8 o'clock. Meet my best team member. That is Suraj, that's been helping me set up the Zoom for our biocosmology press release live from Everest Base Camp. It's a beautiful day. I thought before I start the science, I will just show you the mornings. So we just have a helicopter over there going back maybe to Lukla or to one of the other cities. We are at 5,300 meters, which is in feet
almost
17,500 feet. And I want to welcome you to the press release of biocosmology. We have had to do it from Everest Base Camp. This has been quite a ride. I am so proud to finally be at a position where we can release these papers. I will explain to you why I started this science and what a ride it has been with my wonderful, wonderful friends, Andrew Liddle, Lee Smolin, and Stu Kaufman, who are
Jumping to a second video now.
So welcome again. Here are minor things. It's all part of base camp life, that the battery goes there. There's no electricity. This is quite a world. If you're not in base camp, I would invite you to come here just to experience how precarious life is here, and at the same time, how beautiful it is. So I was describing our ambition of counting the degrees of freedom of the number of states contained in the biosphere. Suraj, as I'm speaking, you can also do turns, so it's not very boring to look at this in person. So Stu Kaufman had this idea that the next state in the evolution of biological systems is not predictable because there are no underlying laws like we have, for example, for the Lagrangian of the standard model of particle physics. The Lagrangian predicts the next state under some regime of approximation. In biology, this doesn't happen. And so I discussed with Stu quite at length, and we decided to use this TAP equation, which is contained in the papers, and Andrew will explain better. We use this TAP equation, which is pictorial innovation for describing new states formed in living systems, which are not to be predictable from existing states. We started counting the states at 3.7 billion years ago, when the life formed, life first appeared in the universe, and we used the number of genomes, the number of atoms in organic compounds, which is 6. All these genomes molecule has carbon.
I'm glad to stop there because I know there was a lot of wind noise, but I hope you could hear a little bit of what she was saying and get a flavor for our press release, which was really a very eventful thing back in April last year. So turning to the science, what is biocosmology all about and how can I motivate it to you? Well, as I've already said at the start, our goal is to formulate physical laws in a way that directly allows the inclusion of biological systems or living systems. And in thinking about this, we were led to challenge many of the traditional views that you take in the physical sciences, which don't fit very well with the way that modern biology is done and the way that biologists such as Stuart Kaufman think. So when we started this, we weren't sure how far we were going to have to unwind our knowledge. But it turned out to be really quite a long way, because certainly for me, and I think for Lee Smolin, quite challenging to realize that as physicists, we spend a lot of time taking for granted certain things about how the world works. And these might be true, but if you want to understand living systems, you can rapidly find yourself getting into trouble or contradictions that make you feel a little bit uneasy and might make you start to revisit the issue of whether or not the things you believe were really true. And here, I think there are two connected but distinct things I could have said. I put reductionist here because the challenges to reductionism have quite a long history, and they're easy to refer to many precedents for this. Reductionism is the idea, as I've said, that you can understand any physical system by breaking it down to smaller parts. So, for example, you might be able to understand the behavior of a gas and to get thermodynamic laws of how a gas might evolve and understand heat from a microscopic description where everything is described in terms of individual atoms. And where it turns out actually it's highly debatable whether there are any reasonable derivations of thermodynamics on the basis of a more fundamental level. But that's another issue I'm not going to talk about, I think, anymore today. Reductionism is one thing. Another thing to have in mind is determinism. Determinism, going all the way back to Laplace and others 200 years ago, is the idea that the universe unwinds like a Newtonian clockwork model, that you just define your initial conditions, you have a set of laws, and everything inevitably follows from then on forwards. And in physics land, the only significant change to that viewpoint that's taken place over the 300 years since the Newtonian paradigm was introduced is the idea of quantum randomness. So we no longer believe that physics is absolutely deterministic. We believe that it is mixed up with chance occurrences. So radioactive decay, for example, being something that you cannot predict in a fully deterministic way. Yet radioactive decays might well have impact that goes well beyond the quantum world. Radioactive decays might be responsible for a world leader contracting cancer, for example, and dying prematurely. And in one quantum universe, the leader dies, and the other one, the leader doesn't. And the future of the world can be very different from then on in. So quantum mechanics undermines to some extent determinism, but only in a random, unpredictable way. And that is, I think, the modern physics view of how things work. So those are the views that we've had to go back and think about, and I'll say a little bit more about that in a minute or two. But I want to say as well, our starting points, the idea that Marina had, was that we would try to quantify the value of the biosphere in a physics language, the language of information, states, and entropy, to try and enable it to be compared with the more traditional physics things that everyone knows how to handle, the information content of black holes or dark matter or even dark energy. So the terminology is the currency of the cosmos. We want to try and put biosystems into the currency of the cosmos that we all understand as physicists. Now, more on reductionism particularly. I just want to get you thinking a little bit about this and see what you think. Different people, I think, have different views, and you're all entitled to your views. You're entitled to change your views as well, as people sometimes do. So I think the audience is probably entirely physicists. Unfortunately, I can't see the whole audience list to know, but I'm going to presume that the audience is essentially all physicists, and I'm a physicist. And we are all believers in some ultimate supremacy of physics as a discipline, I think. We come to physics because we think it's the fundamental science. Often we can be a little bit disparaging about our chemistry colleagues because we say, well, chemistry is just some form of applied physics. It's all the Schrödinger equation in some complicated circumstance that's maybe hard to solve, but we're sure that if you were just had a bigger computer, all of chemistry would just work out as some kind of solution to physics. Then you think about biology and you say, well, biology is really all just chemistry. You know, these molecules are super complicated. They're put together in really, really tricky ways into cells, and the sorts of interactions that go on in the cells are extremely complicated. But it's all driven by chemistry. And chemistry is just physics, so biology is somehow also contained within physics. I think probably most physicists believe this. And if we're in a lecture theatre, I'd ask for a show of hands, I think, how many people do believe this, but I'll just let you think in your own head. Do I think this is right? Physics is the supreme science, and everything else follows from that. Now, there are various challenges that come to that from biosystems, but another way to ask this question is just to ask yourself, if you live your life according to what I just wrote down in that first paragraph, do you live your own life as if the future is already predetermined by the laws of physics? Or instead, do you actually think that you have some freedom to predict what you might do, that you can change your future, you can decide which model of car to buy, which seminar to attend, which thing to order off a menu? In their everyday life, everyone acts this way, I think. Everyone behaves as if they have a notion of free will or agency, even if simultaneously in some other part of their brain they're holding this physicist view that actually that can't be true. Instead, everything I do was determined by the configuration of the atoms in my body and in the surrounding area as I got out of bed in the morning. Philip, I see you have a question. I'm just going to finish my next point to end this thread so that it's complete. Now, one way out of this dilemma is that many people claim that actually free will doesn't exist and it's an illusion. But even they, I think those people as individuals do not act as if they really believe it. For example, you can read books of people who say that free will is an illusion and actually you just carry out, you're compelled to carry out your life however it's done. But in their books, they're still essentially bragging about how they've worked this out, and they're presenting the conclusion to you in a book, and aren't you stupid for not seeing that this is the obvious conclusion that follows from the premises they've given? But if they are correct, they have no right to brag about this conclusion because their very beliefs were laid down long before they were born, in principle laid down at the onset of the universe from which everything started. And yet they, as academics, they feel they're unable to deny themselves credit while denying free will. Okay, Philip, I see you have a question. Sorry, I waited a long time as I like to finish this little spiel before letting you come in, but go ahead, please.
Yes, well, first of all, good morning, Andrew. Secondly, I think that with the anthropic principle, physicists are beginning to recognize that biology is an integral part of physics.
I think that is true, and that's true at a kind of an inferential level, if you like. So it says our existence or the existence of atom-based life can be used to infer certain things about our universe and how it must be. And obviously there are different incarnations of the anthropic principle and different levels of belief. And I think, to me, the weakest version is kind of self-evident that the universe has to be suitable for hosting molecular-based life, because we are molecular-based life and we are witnessing the universe. Whereas the stronger forms that say the universe demands to have life within it, I can see no scientific basis for them. So I approve of the weak anthropic principle, at least, but I'm dubious that it has very much in the way of scientific content. In biocosmology, I think we want to push further than that by not directly connecting life to the universe in the way the anthropic principle does, but rather trying to take lessons from how life works and asking, do these have implications for how we understand the universe? And the answer might well have been no, but we think there are good reasons to think that the answer might be yes, that formulating physical laws in a way suitable to consider living systems may cause us to reconsider how we model the universe as a whole. Thank you. So,
Can I ask a question?
Yes, please do.
Well, I have two questions. First question is, when you said cosmology, what comes to my mind is first of all, there is already a field called astrobiology. So how how these two are different.
So astrobiology, I think, it's a very useful question. I probably should have clarified. So astrobiology is people investigating conditions in which life can arise, both in our solar system and in other solar systems. So I think it's sort of an observational science of saying, what are the circumstances in which life comes into existence? What kind of environments does that happen in? On what timescales? It's a kind of discovery science at the moment of the transition from non-living to living, which is certainly not understood even on Earth, far less anywhere else. Biocosmology is specifically cosmology rather than astro, because we're not trying to look at environments. You don't learn about biocosmology probably by looking at an exoplanet and discovering whether it has some kind of bacterial life on it. It's a question of understanding physical laws in the context of life and taking inspiration from what we see in living systems. So
Okay.
that was the first question. I hope I've answered okay. I think you said you had a second as well.
Yeah. So just related to that, because you mentioned dark matter and dark energy. So I was quite fascinated by a book by Lisa Randall on dark matter and dinosaurs. So is it in that line, like your line of thought of biocosmology? I hope you know the book.
I'm aware of the book. I haven't read the book, but I think it claims there can be some connection between the existence of dark matter and the extinction of the dinosaurs. Is that correct?
Yeah.
There. I wouldn't say it was the same thing in a way. That's again, it's like an astronomical phenomenon. I don't see that a bunch of dark matter extinguishing the dinosaurs is conceptually very different from a big asteroid destroying the dinosaurs. It's some phenomenon that's happened in our past at our location, which has had serious implications for life on planet Earth. But I can see it. I mean, if it's a way of learning something about the properties of dark matter, then it's a useful probe. It's still not certain it's getting to the level of asking how physical laws operate. But I'm maybe not familiar enough with the book to be able to answer that very well.
Okay. Well, what she predicts is that somehow about guessing that what must be the dark matter distribution or motion of the solar system within the galaxy. So basically, this I understand, like to see how dark matter is distributed. Well, it's a fascinating thought, but I'm still missing, because biology, when it comes to biology, it's all with some planetary system or solar system or within life within a galaxy. Cosmology is wider for wider scales. So I'm just puzzled how you connect these two, biology and which is local, which is related to science of local systems, and cosmology is too wide.
Well, I hope to convince you of some directions in that during this talk. So perhaps at the end, if you're unconvinced, you can ask me again.
Okay.
Just check how I'm doing for time. Okay, I think I'll press on a little bit. Yeah, I should say I'm giving a very brief summary of things which are in our papers, but mostly in the first paper. I'm not really even talking about the second paper at all. There's a lot more detail and background in the papers if you should want to read them. Okay, let's move on. So our entry point into thinking about biocosmology, the thing that led us there, is to consider the information budget of the universe. And so I wanted to remind you or tell you how the information budget of the universe is traditionally worked out and what the relevance might be for life here. So I have many of these slides were borrowed from Marina. This is the first one of these. I think, as I already said, the goal is to seek a common language, in this case using the number of states of different systems as standard currency. This allows us to translate between physical systems that we're familiar with and biological systems that we may not be. So the problem here in the minds of the cosmologists is the initial conditions of the universe and how the universe began. And this is usually formulated in terms of the unexpectedly large entropy of the present universe. And Roger Penrose has been particularly articulate on this for a very long time, and there's a huge discussion of it in the Road to Reality textbook that he wrote. So one of the key questions about the universe is to try and think, why was its initial condition so unlikely, given that the present universe represents a huge number of possible situations that the universe could be in, which we can quantify by calculating the entropy. And this is something that's evolved over the lifetime of modern cosmology, more or less. So in the 1980s or so, 1980s, people like Kolb and Turner were interested in computing the entropy of the universe, and they focused on the material content of the universe. And it became apparent that if you did that, the largest entropy, which we can measure in our observable universe, is a number for our observable universe. The largest entropy is associated with the photons in the universe. And the relativistic particles more or less contribute a degree of freedom per photon or per neutrino. The cold material, like the baryons and the cold dark matter, contribute much less entropy. So the entropy in our observable universe from its material content is given just by counting the number of photons in the observable universe. The answer is about 10 to the 90 photons. And so the number of states is the exponential of that. So something like 10 to the power 10 to the power 90, quite a sizable number. But already in the early 1980s, it was realized that there are other bigger sources of entropy in the universe. A guy called Frautschi was the first to point out that the supermassive black holes, already known to reside within galaxies, gave a bigger entropy based on the Hawking-Bekenstein entropy formula. So our own Milky Way has a 10 to the 6 solar mass black hole in the middle. If you assume all the galaxies have 10 to the 6 solar mass black holes in the middle, you add up the entropy, you get something a bit bigger than 10 to the 100. So 10 orders of magnitude bigger than the photons generate. More recently, that number even has been revised up a bit because people have become aware that there are much more massive black holes. There's a 10 to the 9 solar mass black hole in M87 that the Event Horizon Telescope imaged recently, for example. And that's pushed the number up to maybe 10 to the 104 or so as the entropy of all of the supermassive black holes inside our observable universe. And it's pretty much dominated by the most massive black holes that exist. The black hole mass function turns off eventually exponentially sharply, but only at very high masses above 10 to the 9 solar masses. And because the entropy goes as the mass squared, you tend to be dominated by the most massive black holes that you have. And so whatever you think are the most massive ones in the universe, that gives the biggest contribution to the entropy. So 10 to the e to the 10 to the 101, or maybe e to the 10 to 104 was the state of play in the 1980s, early 1990s. That changed again when it became widely accepted that the universe featured dark energy or a cosmological constant, for example, from Saul Perlmutter's discovery of acceleration of the universe through supernovae, along with Rees and Schmidt. The discovery of dark energy or cosmological constant implied that there's also a cosmic horizon. The cosmic horizon is much bigger than any of the black hole horizons, and although its interpretation is a bit more controversial, it was pointed out in the 90s first by Paul Davies and then by many other people that the entropy of the cosmic horizon is a much bigger number again. It's roughly 10 to the e to the 10 to the 124. So completely dominating over all the other sources, vastly more than any of the material content of the universe. So the entropy of the universe, the observable universe, is a number, something like this, according to best present understanding. For quantum gravity people, this would also be recognized as the holographic information bound for our observable universe, bounded by its event horizon. So, where does this take us? Well, nothing in the discussion I've just given you has paid any attention to the existence of life. So it's considering a dead universe, nothing very interesting going on, no evolution of complex systems. whatever happens at the start, everything was laid down and evolved according to relatively simple physical laws. That still gives us this huge problem of initial conditions because the entropy is 10 to the 124. So the number of possible states in the universe today is huge. The early universe was very, very special within that huge number of states. And it's very difficult to explain why the universe started that way. But this is not something I feel I have a deep understanding about, but it's normally assumed under the name of the past hypothesis that the universe was of some extremely special form at an early stage. And then this is hoped to give rise to some cosmological arrow of time as the universe evolves to the high entropy state that it has at present, and is presumably on the route to yet higher entropy states in the future. But we've not talked at all about life as yet. And I think the reason why people haven't talked about life is quite simple, that if you only think about it for a few seconds, it's very easy to conclude that life cannot possibly give a significant contribution to the information content of the universe. Why is that? It's because the information content of the universe is supposed to count all the possible ways that you can assemble all the material in the universe. So it gives you every possible configuration. People like Sean Carroll have been very keen to emphasize this. It's an enormously large number that contains all the possibilities for how you put together the materials you have at hand in the universe. So the Earth is represented in there in terms of the locations of its different atoms. So given that the Earth or other planets generally in biospheres contain such a tiny fraction of the material that's in the universe, it seems completely self-evident that they cannot make any significant contribution to the information budget. That is what we are challenging with biocosmology. Sorry, this is actually just restating what I just said, that it seems that the smallness of our planet means that it can't possibly make a large contribution to the number of microstates in the present universe. Another thing that's made it hard to ask this question, how do you quantify life in biology, is the lack of laws. In physics, we're very happy usually because we think we've got a bunch of equations that we can deal with, so everything is unambiguous. Here's the Lagrangian of the standard model, and sure, it's complicated and a bit nasty looking, but it's a calculable thing where you know all the different degrees of freedom and how they interact with each other. So physics laws in that way are simple. They may be effective. The standard model may be just an effective theory of some more complicated, or actually maybe some more simple higher energy theory. There may be effective theories coming from the standard model, like atomic physics and molecular physics, which are occupying different regimes. But that's the nature of physics, to go through a sequence of effective theories that enable you to describe different regimes. In biology, there appear to be no equivalent laws. There's no laws of motion for biology. In particular, there's no predictability, or what Stuart Kauffman calls pre-stateability, of what happens next in biology. And one of the reasons for that is that biology is really all about functions and how different organisms can interact with each other. And this happens in a way that you can't predict, because things appear, they get repurposed for other types of interaction. Favorite example that Stu likes to mention is the development of a swim bladder in a fish. The swim bladder is an organ which gives the fish buoyancy by letting it take in and out amounts of water. This probably developed from some other organ, first of all, but when it did develop, it created a new environmental niche, and inside that environmental niche, a whole new bunch of biological organisms were able to evolve, essentially forming a kind of fish bacteria bound state, if you want to say it in physics language, bacteria that can only live within the swim bladder of a fish and have no existence otherwise, and can do so either to the mutual benefit of each species, or can do it in a parasitic way where the fish is harmed, but hopefully not enough that the entire environment is destroyed. So the way that life evolves and biosystems evolve appears to be intrinsically unpredictable. And so there are no laws underlying biology. And although there are principles such as natural selection and evolution, these have no predictive power for telling you where a given biosystem will lead. So to give some concept of how this develops, Stu Kaufman invented this theory of the adjacent possible around the year 2000, I think. Around the year 2000, but mostly publicized best within his book Reinventing the Sacred around 2008. And I already described that the concept here is the rippling of actuality through a sea of possibility. And he devised an equation to try and describe this, which has become known as the TAP equation. TAP being theory of the adjacent possible. It's caused a bit of confusion because unfortunately there's already an equation in condensed matter physics called the TAP equation, which is entirely unconnected to this TAP equation. But this is the equation of the adjacent possible. And as I've said, it's being applied in quite a wide range of circumstances, including economics, environmental science, inventions, and growth of economies. So I've put the equation here. It comes in many different forms, but the idea is relatively simple, I think. So M here is the number of things you have, and T is the time. So the idea is that you want to know how many things you have, be maybe organisms, for example, at time T plus 1, given how many you have at time T. Maybe thinking of inventions is a better idea at this point. And Stu's idea is that what you do is you take the set of all the things you have in a basket, and you can combine them in not any different way you like. And so the last term there is the combinatorial, where you take I elements from your set of things and you stick them together in some way. So it may be assembling things to make a space station, for example, or an airplane, something like that. What are the different pieces you need to create a new thing that's never existed before? And you can put together any number of these things. So you might make a new invention that requires 2 of the existing things, or 3 or 4 or more. It could require all of them, in which case the sum goes all the way up to MT. And the only parameter that appears in this equation is these alpha i's, which give a kind of suppression factor for how hard it is to assemble objects with larger numbers of components. So you might find that it's, a typical invention. If you go and look in a patent directory and you try and figure out what is a patent, most patents take the form of putting together some existing ideas to create something novel. And it has to be novel enough to be recognized as such in order to be awarded a new patent. But usually a patent doesn't come from nowhere. It comes from a combination of pre-existing ideas. Usually it doesn't involve an enormous number of pre-existing ideas because it's very hard to combine lots of things. And this alpha I would be a decreasing function of I that represents how hard it is to combine more and more things.
Excuse me. These are 5 integers or not?
In this version of the equation, everything is integer. Now there are a few issues around this. So if your alpha i's are not integers, then you're in danger of getting a non-integer outcome. You can deal with that. You can either partly solve the equation in some circumstances. We have analytic solutions for various functional forms of alpha I. You can solve analytically and then make an analytic continuation to real valued MT. So that things are appearing. So you're basically allowing yourself fractional inventions. That's the approach we've used because we like mathematics, and I think it's mathematically elegant. The economists who worked with this prefer to create a kind of stochastic version where everything's done in probabilities, and you have the alpha i's. If the alpha I is 0.01, it's interpreted as 1 time in 100 you get the object, and 99 times in 100 you don't get the object. And they run Monte Carlo simulations in order to follow the evolution of the system that way. Ultimately, essentially getting the same result.
I see. Okay. Thanks.
So it's a nice equation. We have a third paper, I think I give the reference or the title, at least in the next slide, that does some analysis of this equation because it's hardly been looked at in the mathematical literature. The key thing about the equation that makes it unexpected and gives rise to some surprising conclusions is that the upper limit on the sum is MT, is the number of objects, meaning that as you create more objects at each step, you then have a bigger basket of possible objects to select from for the next stage. And what you find is if you take the alphas equal to 1 and you run through this system, it blows up almost immediately. Essentially, at each time step, you get the MT raised to the power so MT is exchanged for 2 to the power MT if the alphas are equal to 1. So it starts looking like it's going to be slow, but then suddenly it goes sort of 28, 10 to the 28, 10 to the 10 to the 28. And within literally a handful of steps, if you set the alphas equal to 1 and allow all possibles to come into existence, you get very, very rapid blow up. Now, in this discrete equation, everything stays finite forever. You can, in principle, compute it into the infinite future. But in reality, it blows up so quickly that you can't justify the discrete approximation. And you find, in fact, any continuous equation to which this is a discrete approximation, the continuous equations always blow up within a finite time. So you have extremely rapid growth of MT. Now, kind of interestingly, or maybe worryingly, if you apply this to economic data, for example, the GDP of the world, which has been done over a period, is known for roughly a period of 2,000 years. The GDP of the world stays very close to zero for almost all of the history of civilization, and then only within the last tens of years has it undergone an extremely rapid rise, which of course is good because it means people are getting richer. But economic growth also drives environmental degradation. And if you look at any number of environmental indicators, they also have the same pattern, like the CO2 in the air, but all sorts of pollutants and other things. Again, stays very, very constant for essentially all of recorded history. And then within the last few decades, starts to shoot up extremely rapidly. And the TAP equation provides quite a reasonable model of these different processes. Which is, at least in the environmental context, very, very concerning indeed, because it suggests a possible that we're in a rapid runaway phase, which has perhaps been presaged by people who talk about a singularity. If this in technological advance, that technological advance seems to be getting faster and faster, and rather than just being exponentially fast, it's actually super exponential with a finite time divergence, as some people like Ray Kurzweil have argued. And TAP has that kind of property about it. For environmental purposes, you have to hope that it's, even if it describes what's going on now very well, that it's an effective description, which had better not keep describing what's going on into the near future, because if it does, environmental catastrophe will be very, very sudden and very, very catastrophic, much more so than normal climate models suggest. Anyway, this is the theory of the adjacent possible. It has the freedom of parameters of the alpha I here. There are also different ways to tweak the equation. I personally like to start the sum from 2 rather than 1. I'm not sure why in the original version Stu Kaufman had the begins with 1, but I think I do know. If you start with I equals 1, you're saying that you're going to make something new just from a single existing item. So it's trying to allow that a single item can evolve into something new rather than being combined with a different innovation to create something new. Anyway, there are different versions of the equation to deal with that we want to explore. So what are we going to do with this? Well, this is going to tie into the non-reductionism, and in particular, the concepts of emergence in complex systems. So first of all, physicists of the kind I'm used to talking to, which is essentially particle physicists, gravity physicists, cosmologists, all of us believe in fundamental physics predominantly. But it turns out that you don't really have to go very far within the physics discipline to meet very renowned people who don't believe in that at all and make very compelling cases that we shouldn't believe in that. Three very good examples are the condensed matter Nobel laureates Philip Anderson, Tony Leggett, and Robert Laughlin. They all have Nobel Prizes, and all of them have stressed that condensed matter systems do not appear to be predictable in terms of underlying fundamental physics. Anderson very famously wrote an article called "More is Different," where he espoused this view and stressed or stated that to understand condensed matter systems, you have to posit physical principles whose status is every bit as fundamental as those that are dealt with by people making theories of particle physics or quantum field theory. Tony Leggett makes a similar point in arguing that he argues that no one has ever successfully derived condensed matter phenomena from a simpler reductionist level of reality, with essentially putting in the right answer by additional assumption. And he cites several cases of this, in fact, where people have thought they successfully explained some phenomenon, and the experiments had turned around and given exactly the opposite result, what people thought had been true. And immediately the condensed matter theorists just tweaked the assumptions they were using in their derivations and could produce the completely different, but now observed phenomenon from some microscopic description. And he argued that, in fact, no one ever really derives anything from first principles in condensed matter physics. Robert Laughlin makes a similar, or at least related point, but noting in particular that in a lot of condensed matter systems, phenomena do not have a reductionist view because they disappear if you make the system small. An example of this is superconductivity. You cannot understand superconductivity by making a smaller and smaller superconductor and trying to eventually analyze a few atoms to try and see how they're superconducting, because superconductivity is a collective phenomenon of the entire material that you're dealing with. And if you make the material too small, the phenomenon of superconductivity will simply disappear. And he argues that many other phenomena in condensed matter physics are of that kind as well. And that every time you want to try and understand these kinds of phenomena, you have to add in extra assumptions or principles that are in addition to whatever you've stuck into your Lagrangian. Now, that's all just within physics, but of course, biological systems and living systems are exhibiting far, far greater levels of complexity than anything that's ever dealt with in condensed matter physics. Even an individual organism, that would be true, but a complete ecosystem like the planet Earth, all the more so. The complexity and the non-ergodicity of the biosphere is absolutely colossal. So how does biology deal with this? Well, in biology, functional explanations are seen as essential if you want to have any idea of what's going on. And what's meant by functional explanation? Well, the simplest thing to consider is your heart. Your heart's in there, it's beating away quite happily. And everyone would agree that the heart is behaving according to some laws of physics. Ultimately, there's no violation of physics in your heart. It's beating according to some electrochemical signals moving around inside, and pumping the blood, which is moving according to some viscous fluid mechanics laws, etc., etc., etc. But none of this will let you explain why you have a heart or why hearts exist at all in the biosphere. Because the existence of hearts has nothing to do with whether they're compatible with the laws of physics or not. Hearts exist because they have a biological function to pump blood in a larger organism. And the only reason hearts exist in the universe is because in doing so, they can provide evolutionary fitness to some larger organism that will allow that organism to survive and be subject to natural selection, which for it will be in a positive way. There's a language for this which Stuart Kauffman introduced us to, which is a Kantian whole. This is Kant as in the philosopher and whole as in a complete object. The Kantian whole is a collection of objects which exist in order to provide the functions that enable the larger object to exist. So you as a person are a Kantian whole, and you provide the environment for your various organs, which could not exist in isolation of your body. So this kind of explanation is used in biology. And from the point of view of biocosmology, what we propose or posit is that the evolution of biological functions creates new biological states. So the model we have in mind here is that the reason why biology is not pre-statable and you can't predict in advance how a biosystem is going to evolve is that it is forever creating new unpredictable biological states. And this creates a very different paradigm to the one that physicists are used to, where you have a fixed Hilbert space or state space, and evolution is happening within that according to some Hamiltonian law or Liouville theorem or something like that. In biology, there's the possibility that you have these functions continually being created, and the adjacent possible is a model for how functions can interact and create new functions in new environments together. So our proposal is to use the theory of the adjacent possible to compute the number of states. And we've done that this is in our paper 1, but we've also put a bit of mathematical background in a third paper analyzing the TAP equation. And this is just an example of a run that shows you the sort of behavior you get for some particular values of the parameters. This is a slightly more complicated version of the TAP equation. The alpha I, these coefficients I had, they're going to fall off as a sharp power law. The A is the power law. And we're also going to allow for an extinction term as well, which wasn't in the version which was written before. The extinction term is given by the mu. But anyway, this is the formula. And it shows the growth of the number of states as function of time. The main graph shows the hockey stick curve of it coming up, which looks a lot like a GDP curve or an environmental catastrophe curve, especially bearing in mind the exponential y-axis. But the growth becomes exceedingly rapid towards the end, and the inset graph shows just a single additional step, which revises the y-axis of the graph from going up to 10 to the 5 to instead going up to 10 to the 206, or I think it's 10 to the 240, something like that at the end. So the growth and the blow up at the end of the TAP process is extraordinarily rapid, and viewed on that kind of scale, you just see it as basically flat with a single sharp jump at the end. That's another way you know it's much steeper than exponential. If it was exponential and I did this, then you just see the same graph repeated over and over again because the rescaling of the exponential gives the same exponential. So what we find is that using a TAP equation, you can get these extraordinary super combinatorial growth of states. So how does this fit in? If we take that to be an estimate of the way that living systems can behave, well, the standard answer in physics is the number of states is 10 to the 10 to 124. In one of our simulations, we found this number 10 to the 10 to 237. That was the number you saw on the slide that was just there before. Now, absolutely, you should not take the 10 to the 10 to 237 seriously as a number. I could change the alpha by some tiny amount and get a completely different answer. I could run it for a different amount of time and get a completely different answer. There's no meaning to the actual number which is being quoted here. So don't take the number seriously, but what you do need to take seriously under these circumstances is the vastness of the number, 10 to the 10 to the 237. So under these assumptions that I'm making, growing state space, functional evolution of states, the living system behaves in a way which is very different from a normal physical system and can give rise to a huge number of states. So in our analysis, we started out thinking that the cosmos was some enormous number of microstates and the living biosystem was essentially zero in comparison, and finished up with some completely different concept where it appears that the biosphere can have an enormous number of microstates associated with it. So that's what we've done in the first paper, is take this new paradigm, push it to its limit, and try to give a value to life based on how these laws are working. I want to end with because it was in the abstract. I thought I might run out of time, but it's in the abstract. I want to talk about this. This all ends up with a very extravagant proposal, and if you asked me, I would have to say I don't think I really believe this, but on the other hand, it has a kind of compelling logic to it that meant that I couldn't resist talking about it here, and we made sure that we had it in the paper. That if we've made a calculation which shows that life can develop all these extra states, can there be a cosmological effect associated with it? And the effect that we're interested in is the effect of a possible dark energy type behavior. Now, one reason why that's not absolutely ridiculous to think about is that there is a very strong coincidence between the onset of dark energy domination in the universe and the onset of life. And many people have talked about a coincidence problem in cosmology, which is why is the cosmological constant just coming to dominate at the present epoch. The coincidence is actually even stronger if you ask what was the value of the cosmological constant at the onset of life on Earth, because the redshift of the onset of life on Earth and the onset of cosmological constant domination are almost identical. It's a second decimal place thing. But anyway, the appearance of life in the universe and the appearance of the cosmological constant are more or less contemporaneous, and that's a puzzle that we've all been trying to solve in various ways over the years without any success whatsoever. So does biocosmology offer any thoughts to this? Well, if living systems can create large numbers of states, is there any physical reality to these states that might connect to dark energy? Now, states in quantum theory, of course, have zero-point energy associated with them. The cosmological constant that we worry about is probably coming from the zero-point energy of quantum fields. We're positing a changing number of states, and might those new states have an energy density associated with them? For example, are they draining energy from other forms of matter into something which is behaving like a vacuum or zero-point energy state, and thus creating some kind of dark energy phenomenon? There are some ideas along this direction which might be equivalent to what I'm saying, but I'm not certain, which is information theory-based models of dark energy. A guy called Philip Goff has one, for example, where he claims that information erasure in fusion-burning stars gives rise to a Landau entropy, which is comparable to the what is required to explain the acceleration of the universe. What I'm saying is maybe similar to that. Perhaps more straightforward and quantum gravity kind of way to see there might be something going on here is that many of you will already have noticed that I'm talking about a number of states which is much bigger than the 10 to the 10 to the 124 of conventional cosmology. That number, 124, is supposed to be the Hawking-Bekenstein entropy of our cosmic horizon. And in the interpretation of holographic theories, that is also the Bekenstein bound that limits the number of states which can exist within our observable universe. So biocosmology is claiming a number of states which is in conflict with the traditional Bekenstein bound applied to the cosmic horizon. Now, we're thinking very hard about how to resolve this. We've been talking with Raphael Busso this summer, Paul Davies and other people. A simple way to say there isn't really a conflict is to realize that the Bekenstein bound is derived under assumptions which are violated under cosmology, particularly the fixed state space. Also, we don't know whether the biocosmology states are gravitating or not. So it may just be the traditional Bekenstein bound doesn't apply. But another possibility is that instead, the number of states will actually back reacts on the cosmic horizon. And this is an interesting interpretation of the holographic principle. It comes from work of Tom Banks, especially around 2003, I think, more or less, and interpreted by Raphael Busso, is that one should write the Bekenstein bound the other way around, that the number of states is the fundamental quantity, and the horizon has to do whatever it has to do in order to be consistent with the number of states, in order that the Bekenstein bound is not violated. So in that picture, combined with biocosmology, the growing number of states created by biocosmology has to back react on the cosmic horizon in some way, and it should do so in such a way as to prevent the Bekenstein bound being violated. It would then clearly be compelling that the Bekenstein bound is saturated in that way, because whatever the back reaction mechanism is should run into the Bekenstein bound and then stop. So it's very much consistent with the idea that our universe has a Bekenstein bounds worth of states within it. And that way of phrasing it, I think, is probably equivalent to argument 1 above, but is in a more traditional quantum gravity kind of language, I think. In any case, this is all highly speculative, but it's worth me pointing out, there's many ways to object to this. And certainly some of these objections, I think, will require that life is widespread in our universe. Life on Earth alone cannot possibly be responsible for the kind of phenomenon that I'm talking about. It doesn't happen early enough, and it doesn't happen in enough places. You can certainly find principled objections to it, but in some ways you don't have to know how to deal with them to explore the scenario further, because the scenario definitely makes a prediction that dark energy should turn on at some point during the young life of the cosmos, young stage of the cosmos when life first appears. So rather than the lambda CDM model where the cosmological constant has existed forever, we have a model where there's no cosmological constant up to some point. It turns on possibly relatively rapidly and then saturates into a cosmological constant value. That means that at least for some phase of cosmic evolution, the cosmological constant will behave like a phantom dark energy with equation of state less than -1, I think, during the turn-on phase. And I might as well mention that observations such as they are certainly consistent with lambda CDM, but persistently show some modest favoring of the phantom dark energy models rather than the non-phantom dark energy models. So it's relatively easy for me to believe that if we go away and analyze this proposal against observational data, that it will do at least as well as lambda CDM and may do even a little bit better than lambda CDM against the data. I'm almost done, but I think I'll take the question from Philip first, and then I'll summarize and finish.
Let me see, am I live? Yes. When you say that the onset of life and the onset of the cosmological constant are the same, that would require that the onset of life all over the cosmos would be at the same time, not just the onset of life on our particular planet. And we don't have any evidence for that.
We don't have any direct evidence, but I think I certainly, it is not, Earth alone cannot do it, because the dark energy comes to dominate it at the time life starts on Earth, but it's observed at higher redshifts as well. Before it becomes dominant, it already has a non-negligible effect on the expansion rate of the universe. So it has to begin earlier on. But on the other hand, so that's what I mean by saying you have to believe that life will be relatively widespread in the universe. But if you do accept that life's relatively widespread, and there are some new ideas in theoretical biology about pathways to life through autocatalytic sets that suggest it might be easier for life to begin than had previously been thought. If you just accept that life is relatively easy to form and is widespread in the universe, then a reasonable proxy for the amount of life in the universe is the star formation rate of the universe, which is relatively well determined, because that is more or less a proxy for models of the universe, is more or less a proxy for the number of habitable planets in the universe. Sorry, my phone is ringing, but it's too far away for me to reach. So I would do this calculation using the star formation rate as a model for the onset of life, and star formation rate peaks more or less at redshift of 2 or so. So prediction is for dark energy to turn on more or less at redshift 2. This is actually what Paul Goff uses in his information in stars argument for dark energies. He uses exactly the star formation rates to get a model to do that. Okay, I only have one more slide. I'll let the chair decide whether I should do more questions now or whether I should finish the talk and then take questions.
Okay, please, you can use your last time, last slide.
Okay, just to summarize. So to say again, what is biocosmology all about? The way we came at this is we want to formulate physical laws that allow for the way that life behaves. And it's led us down a path of challenging the reductionist view of physical sciences, which so much of modern physics is rooted in, but doesn't seem very compatible with the way that living systems behave, or even individual human beings behave. And so that invited us to revisit the question of what is the appropriate physical underpinning that we can use to try and describe how the universe evolves. So we want the thing we've started with is trying to use the information of the universe and try and quantify life in that way. And we came across these very useful tools coming from Stuart Kauffman and his collaborators of combinatorial innovation and the theory of the adjacent possible, which are becoming very widely used within theoretical biology, but also social sciences, and give a very different kind of view as to the processes which are relevant. I should say I'm relatively restrained here. Stuart Kauffman has very strong views on also more or less the end of physics, as he says that the era of physics is over because biological systems simply cannot be described within the framework of physics at all. I think the rest of our collaboration, Marina and me, certainly don't think that. Instead, we want to try and push physics to be able to capture more types of behavior than it's traditionally been doing. And so to try and advance physics through these new technologies like combinatorial innovation to try and be able to address living systems. So anyway, we made some assumptions. I have not spelled them out in great detail. You can find a lot more in our published papers, but leading us to the belief that living biospheres may give a much bigger contribution to the universe's information than has previously been believed, and indeed may even be the dominant one. So that's where I'll end. Thanks very much for your attention.
Okay, thank you very much for your very interesting talk. Questions. I see questions from Richard Kerner. Richard, please ask your question.
Yeah, it's maybe not a question. Thank you. It's a suggestion. You know, that there was an idea in the 19th century by German biologist Ernst Haeckel. He put forth the idea that ontogenesis is repeating phytogenesis, or it means that if you follow the evolution of single living creature, then you can observe how the whole species evolved. For example, you start like a little amoeba, and then a little fish, and then little. You see the embryo is following. So maybe you can explore the idea that life on Earth, that the story of life on Earth is in a way repeating the story of cosmos itself.
That's interesting. Certainly, Stuart Kauffman, I think, is very much of the opposite view in saying that you cannot predict anything in advance. All you can do is try to explain what has happened in the recent past through various forms of functional explanation. But that predictive, he would say that predictive
for
power
example,
is,
if you
is
follow,
absent.
if you take it seriously, if you follow the evolution of a single human being, then you can arrive to conclusion that the universe will die. For example. And there's another thing I would like to, perhaps you know the science fiction by Arthur C. Clarke. It's called 9 Billion Names of God.
Yes, I remember reading it as a child.
It's an example of how things here on Earth can influence the cosmos.
Right. Yes, in the end, the whole universe dies, doesn't it?
The hypothesis was that once we know, well, he was extremely modest as compared with your numbers. 9 billion is just nothing. 9 billion names of God. They have set a computer to accelerate, but once they knew, it turned out that the universe is starting to...
The universe's purpose ends and it is disassembled and packed away.
Yeah, and the universe is going to disappear too. Okay, that's just a comment.
Yes, thank you.
Okay, I see the questions from Gaetano Fiore.
Yes.
Gaetano, please ask your question.
Yes, one question and one comment. I've not really understood how information is encoded in the functions of living bodies, living creatures, because as far as I can understand, the number MT which you introduced with this top equation counts how many ways you can combine things, and I think you were combining somehow again, I don't know, molecules or atoms or something like that, which you said would not give a large enough contribution to the information. So how do you really increase the number of states in microstates in biology? I have not understood. Where is information encoded?
Yeah, that is very much something we would like to understand. I think it's fair to we have not understood the nature of the states that we're counting properly. So indeed, they should not be atomic type of states. They should be functional affordance states that come from interactions of different biological mechanisms. Because essentially, this whole treatment is insisting through the use of emergence that a listing of the positions and the velocities of all of the atoms that make up an animal is not sufficient to fully describe that animal. And the extra states are the extra information which is needed to encode whatever functional information the animal represents within its ecosystem. And so while I gave an example of a bacteria in a swim bladder of a fish as a kind of a novel bound state of these two organisms, the binding is happening not in physical space. It's happening in some kind of information space.
Okay, but then your proposal is still then at a stage of inspiration, but not concrete.
Yes, absolutely. We're starting out on a path, and at the moment, the path forward is quite obscure.
I see. And regarding a comment, I wanted to comment about reductionism. I would be not so reductive about reductionism. Reductionism tries to explain more complex phenomena in terms of simple building blocks, which not necessarily are small things, could be also other sort of things, but as few as possible, as in axiomatic theory, in Euclidean geometry.
Yes, I agree. A reductionist in ideas rather than in scale.
Yes, and I mean, the full set of consequences which you can derive from a full number of ingredients is not really predictable a priori, so, and definitively. You can always find something new. Coming back, for instance, to the example of condensed matter physics, you think you have found the building blocks of, in that case, the atomic building blocks of matter. But since you don't know how to solve exactly the equations, you need to introduce some approximations, some model. And you can do this in many different ways. And so in finding the right model, you can express all of your creativity and also of your capability to understand what's wrong and what's right in comparison between the first predictions and experiments. I mean, in comparing predictions and experiments, you can go a step forward in each of them, and there is a continuous interaction. And so you can extract, if you advance, you can extract more and more information. From the same ingredients, you may progress and find new consequences, also qualitatively different consequences for both. You don't know how long. So
yes. Yes, I agree. Yes,
reductionism is not really such a small cage. It's a very large frame which allows to do a lot of things.
Yes,
Okay, so
perfect. Thank you.
this was the comments. So let's go to the next question. I see the questions from Philip. Philip, please ask your question.
Ah, yes. Okay. Andrew, this is you're forcing us to think outside the box, which is very, very good.
Yes, I think we're quite far outside the box.
Yes. I have a couple of comments. One is a physics comment. The 0 point is not the same as the cosmological constant. And people like myself and Giovanni Venturi have been talking about this. There's a 0 point pressure and a 0 point energy density, and they have the same sign. Whereas the pressure for the cosmological constant has the opposite sign to the energy density. That's just a technical comment. But going back to what I was asking you earlier, the onset of the cosmological constant is correlated, as you pointed out, with the onset of star formation. And that can be explained within conventional cosmology. It's not outside the bounds of conventional cosmology. So
you mean
we haven't done it.
There isn't an explanation, but absolutely there's a possibility of an explanation. I agree, and I think in cosmology, the formation of stars doesn't seem to do anything. To me, doesn't seem to have any dramatic effect on the equations describing the evolution of the universe. So I think that the normal technique that I tried for a while without ever succeeding was to use the matter radiation transition to then trigger the appearance of the cosmological constant and hope that there would be a bit of a delay because the redshift difference is still 1,000. But maybe if something, there's at least something dramatic happens to the scale factor at redshift of 3,000 when it goes from radiation dominated to matter domination. And I could certainly believe that could trigger something which caused the cosmological constant to appear, but it's difficult to bridge that factor of 1,000. And I've never managed to make any model that could successfully do that. But it reduces a coincidence which is 10 to the 50 down to being 10 to the 3 if a model could produce it. Star formation, I think, is more challenging, though. The information arguments of Goff, and I think there are other people who have ideas along the same lines, maybe a way to do that. It depends whether you believe information has real physical manifestation or not.
All right. And then my last question was, as a physicist, when I see a curve that suddenly shoots up that much of a runaway, my immediate reaction is that the original TAP equation needs some modification, that it's not valid at those enormous runaway. I mean, you think that it would the equation might saturate in some way.
Yes. So the Bekenstein bound argument I made may be of that kind.
Yes.
So I mean, for example, it may be if the biosphere could reach the Bekenstein bound, that would cause the Earth to become a black hole. That would be a plausible way in which the whole process could be. The universe could say, okay, hang on, you've gone as far as I'm going to let you. We're going to collapse to a black hole now, so you can't go any further and break my bound. Mm-hmm. So that's one way it could be saturated. The biological dark energy idea is a gentler way of imagining there's a saturation where some action on the cosmic horizon comes into play, which would, I think, would have to give some damping to the way in which states were being created, because the cosmic horizon can't be shoved around arbitrarily.
Mm-hmm.
Well, that's I need to do some actual calculations to back that up, but I feel that there may be some content in what I just said.
Oh, thank you.
Okay, I see one more questions. This is a question from Vladimir Anashin. Vladimir Sergeyevich, please ask your question.
Okay, thank you. First of all, I would like to thank for a very interesting talk. And my question is more of mathematics rather than on physics. Can you please show your again your main equation, so to say? That one, yes.
This
thank
one,
you.
yeah. So this is a somewhat simplified version.
Yes. Well, about this alpha. These alpha are natural numbers, right? So
no, they should be less than 1, I think. So
they must all be less than 1, right?
Yeah. So they're real numbers between 0 and 1.
Real numbers between 0 and 1. Okay. Well, actually, what I see here. So they can be, for example, rational numbers between 0 and 1, right? Not necessarily real.
Yeah. Yes, could be. So one model we take for these is that they are they take the form of a power law. So alpha 1 is say 100, then 1 over 10 to the 4, 1 over 10 to the 6, 1 over 10 to the 8. If you have a progression like that, if you take there's some progressions, and that's an example of it, where you can then do the summation analytically, and also then, if you wish, use that analytic solution to analytically continue the equation to non-integer values of MT, because you have to find some way of keeping MT integer otherwise. And that's not very easy to do without using some form of analytical continuation. Our third paper, which called the TAP equation, something or other, that paper describes more complicated versions of this equation and various analytical solutions. So you might find that interesting. And because it's such a new equation to the literature, there's probably a whole pile of mathematical results that could be derived about its solutions, which have not yet been. It's not often you come across a novel mathematical equation which is relatively simple.
So the only conditions on this alpha is so actually we have an infinite series of this alpha, but between 0 and 1. But we must take and so that at every step of iteration, because we actually have an iteration of this.
Yes.
Yes. At every step of iteration, you must get a natural number, right? MT, because MT must be must be natural. So 0, 1, 2, 3, right? So this is the only condition.
Yeah.
Other condition.
Unless you use an analytic continuation argument. So I think if the alphas are integers, then everything's an integer and you have no problems. As soon as you let the alphas not be an integer, the equation as written here becomes ill-defined and has to be replaced either by some analytic continuation to real valued MT, which is what we do, or it has to be replaced by a stochastic equation where the alpha i's are interpreted as probabilities rather than as fractions. And that's what the other people who've worked in the topic have done. Steele et al. In particular is a paper which derives quite a lot of results on that basis. So the equation has to be treated with some care. You can't use it direct. As I've written it there, it cannot be used for non-integer alpha I without some careful thought and manipulation.
So the alpha might be non-integer, or because you said that there must be between 0 and 1. So there are no.
What I will for the alpha I chosen, which is non-integer, what we've done is we've analytically summed that series. Which
there are many ways. There are many ways
to do it. There's many ways to do it, but I analytically sum that series, which then gives that series then gives a non-integer result. But I regard that as an analytic continuation to non-integer MT, and because I've done the summation, there's no longer a sum up to MT, so the requirement that MT is an integer disappears. It's a little subtle, but if you read our paper, I think you'll find
okay, maybe
that we've
because
dealt with it. We've dealt with it well in this analytic way, and the stochastic way may be more appropriate. But gives
because
us,
what
gives
I
the same
see here,
answers.
I see here, well, actually, well, from the other side, what I see here, this equation, this is a standard, equation of iterating of discrete dynamical system, nothing more.
Yes,
Right.
that's right.
That's
Yeah, yeah.
right. Okay. Okay. So I can analyze this equation just by using the theory of discrete dynamical systems.
Yes.
I only want to know the conditions you want, because I can do this in pretty other way than analytic continuation.
Yeah.
So the only condition is alpha is between 0 and 1, and t must be natural numbers, nothing more. And then it has some physical meaning, or I'd rather say biological meaning, right?
Yes.
Yes. Okay. Okay. Thank you. That's actually all I want to know. Okay. I will read your
Okay.
paper about it because, of course, it's very interesting. I haven't heard about this because this is the very interesting information for me. So thank you once again
Yes.
for a very intriguing and at least intriguing talk. I'd rather say,
Okay.
to put it so. Thank you.
Okay.
Okay.
Thank you.
More questions, please.
Okay, I should warn my children are probably about to return from school with the babysitter, so any minute now there will be too much noise for me to continue. But before they arrive, Stravan, go ahead.
Okay.
Okay.
Sharon, do you want to ask a
Hi.
question once again?
Yeah, I have a short
Very short,
question.
please.
Yeah, very short question. I hope it will be quick. Well, as far as mathematical part is concerned, the tap equation is a crucial thing you mentioned in your talk. But well, thinking about biocosmology, cosmology is mainly driven by the Einstein equations mainly. Okay, well, of course, we modify it
Yes.
with a lot of quantum gravity insights, but still, Einstein equations are the basis. So how to make use of Einstein equations for the biocosmology? Do you have?
Well, that, and I think the key. So there's two different things, I suppose. One is whether or not we should envisage any change to the Einstein equations based on the general principles that we are using equations compatible with the existence of life. So not actually using the tap equation to do something to Einstein's equations, but rather changing the principles that underlie the Einstein equations. That we're not doing really at the moment, though. The second, which is the one you're directly applying, is if we've got an equation such as this one, which we're interpreting as showing a rapid growth in the number of states in the biosphere, how do I couple that to the Einstein equation to see a possible effect emerge at a cosmological level? And that's essentially the biological dark energy problem. And I think at the moment it seems somewhat ambiguous to me. One way to proceed with the calculation, which is the one I want to do next, or I've already started, is to turn the Bekenstein bound around so that the number of states becomes the fundamental quantity and drives the evolution of the horizon. And then the scale factor, rather than us deriving the scale factor and figuring out the horizon based on the scale factor, the problem is inverted and you want to extract some particular behavior of the horizon, which is consistent with the growing state space, from which you will infer an A of t. But that A of t then needs to be interpreted in some kind of energy density dynamics, because of course we're not positing energy violation or anything like that. So if there is energy associated with these information states, which is what biological dark energy might imply, that energy has to come from somewhere. So the kind of model we're talking about is an interacting matter-dark energy interaction model, where some small, potentially tiny amount of the energy in matter is continually leaking into the information dark energy sector. And because once it's leaked into that sector, its energy density becomes constant. Then even if it was a very small fraction at early times, you can get some result, I think. So whether that gives something interesting, I don't know, but I see there is a calculation there which ultimately is leading to an explicit coupling of the tap equation into Einstein's equation, which I think is what you're asking.
Yeah.
And the
exactly.
trick is to find a way to do it in an energy conserving fashion, which I think I just outlined a way that can probably be done. But I'm not certain. I haven't yet written down all the equations.
Okay. Thank you, and thanks for that.
Okay. As I understand, there is no more questions. Let me thank the speaker again for his very interesting talk. Thank you very much.
Okay. Thank you very much.
Thank you very much. And don't
Thank
forget to send your nice presentation to Alexei.
Yes. Oh, sorry. I should send it. Did you say?
You know,
Yeah,
I mean,
you can
the
send it to me.
slides.
Yeah, just send it to us, to someone to
Yeah.
Stravan or to me, and we will upload it to the
Yeah.
website.
Okay, perfect.
Perfect. Thank you very much.
Okay, thank you.
Thank
Goodbye,
you.
everyone. Enjoy the rest of your day.
Bye.
Especially those of you
Bye.
who have a lot more of it. My day is done.
Thank you very much.
Very interesting.
Bye-bye.
Okay.
Bye-bye.
I'm leaving.
А мы завтра встречаемся.
Да, мне надо еще до дома добраться. Сейчас
Да.
такси. Уже поздно, уже
Поздно.
достаточно
Спокойной ночи.
поздно. До свидания.